We see the world around us every day, trees, buildings, people. But what are these things made of? If we zoom in, way in, we enter the realm of molecules, the building blocks of matter. But our journey doesn't stop there. Molecules themselves are constructed from even tinier particles called atoms. Atoms were once thought to be the smallest indivisible units of matter, but even they have something inside. At the heart of the atom lies the nucleus, orbited by even tinier particles called electrons. The nucleus itself is a cluster of protons and neutrons. And guess what? Even protons and neutrons are made of even smaller particles called quarks. It's like a never-ending Russian doll of the universe. This quest to understand the universe at its smallest scale has led to incredible discoveries and mind-boggling theories. One of the most profound challenges lies in the very act of observing these tiny particles. The tools we use, like beams of light, can actually alter the position and momentum of the particles we're trying to study. This is where the Heisenberg uncertainty principle comes in. It tells us that we can never know both the exact position and momentum of a particle at the same time. The more precisely we measure one, the fuzzier the other becomes. It's like trying to take a picture of a hummingbird in flight. The flash might illuminate the bird, but it also might scare it into moving. To make sense of the universe's building blocks, physicists developed a framework known as the Standard Model. This model describes the fundamental forces of nature: the electromagnetic force, the weak force, and the strong force. These forces govern how particles interact and behave. The Standard Model has been incredibly successful in predicting and explaining a wide range of phenomena, from the behavior of subatomic particles to the fusion reactions that power the stars. It's one of the most rigorously tested theories in physics. However, there's a crucial piece missing from this otherwise successful model: gravity. Gravity, the force that holds us to the Earth and governs the motion of planets, remains the odd one out. It's incredibly weak compared to the other fundamental forces, and attempts to incorporate it into the Standard Model have led to contradictions and inconsistencies. This is where things get really interesting because the universe loves a good mystery. Einstein's theory of general relativity describes gravity not as a force, but as the curvature of space-time caused by mass and energy. While incredibly successful on large scales, general relativity clashes with quantum mechanics, the theory governing the microscopic world when applied to extremely dense objects like black holes. So, how do we reconcile these two pillars of modern physics, quantum mechanics, and general relativity? This is where string theory takes center stage. It proposes a radical idea. What if the fundamental building blocks of the universe weren't point-like particles, but tiny vibrating strings? Imagine these strings like the strings on a violin. Just as a violin string can produce different notes depending on how it vibrates, different vibrations of these fundamental strings would give rise to different particles and forces. String theory suggests that the universe has more dimensions than we can perceive. Just like a garden hose might look like a one-dimensional line from a distance, but reveals its two-dimensional surface up close, string theory proposes that our universe has extra-spatial dimensions curled up and hidden from our view. This radical shift in perspective has profound implications. String theory has the potential to unify all the fundamental forces of nature, including gravity, into a single, elegant framework. It could provide a consistent description of black holes and perhaps even offer insights into the very beginning of the universe, the Big Bang. However, string theory is not without its challenges. One of the main criticisms is its lack of experimental verification. The strings it proposes are so incredibly tiny that they are far beyond the reach of our current experimental capabilities. Another challenge lies in the theory's mathematical complexity. String theory requires advanced mathematical tools and concepts that push the boundaries of our current understanding. Despite these challenges, string theory continues to be a vibrant and active area of research. Even if it doesn't turn out to be the ultimate theory of everything, it has already provided physicists with valuable insights and tools for exploring the universe at its most fundamental level. String theory is a journey into the unknown, a testament to human curiosity and our relentless pursuit to understand the cosmos and our place within it. Who knows what wonders await us as we continue to unravel the secrets of these tiny, vibrating strings. As we stand at the edge of what we know, string theory represents a beacon of hope and curiosity. It invites us to dream bigger, to explore further, and to embrace the unknown. This is Science of Life. Thank you for watching.